So welcome to the Software and Computing Roundtable of May 3rd. Our topic today is workflow and workload management systems. So we really will be discussing today one of the cornerstones of distributed computing. And we today also celebrate a small anniversary for us. So we counted the number of roundtables which we had since we started in 2016, and today we have our 50th Software and Computing Roundtable. I will shortly share the link to our live notes. So if you have some questions or some comments during the presentations, please feel free to put them in the live notes. And then at the end of each of the presentations, we go through the questions either by raising hands or what is in the live notes. So let us get started. Our first speaker today is Federico Stagni from CERN, and he will talk about one of the workflow and workload management systems we are discussing today, DIRAC. Federico, the stage is yours.
Thank you. Let's share my slides. I think you should be able to see them in full screen.
Yeah.
And
perfect.
I hope my microphone is at the right. Yeah. Right. So thank you for the invitation. So I have been asked by Tor and Paul to introduce DIRAC. To show how we can manage user communities workflows with DIRAC. So I have been the DIRAC technical, this is my formal title, technical coordinator for the last 8 years, I think. So what's DIRAC? This is first thing I will talk about it. Then I've been asked to present what are the features and attributes that make DIRAC a popular choice. And then I take this opportunity also to try and look at why DIRAC is not more popular, and so to also look at what are the current, upcoming, and the future developments that might make it or not more popular. So what's DIRAC? I think that most of the people in attendance probably has seen a version of this slide that one workshop or one chat or somewhere else. So basically DIRAC is a software framework for distributed computing, and we claim to be a complete solution for one or more user community, building a layer between users and resources. So DIRAC is not anymore an LHCb project only. It has been experiment agnostic since 2009. In fact, it was born within LHCb, I think in 2005, and then in 2009, basically, Click, the linear collider, wanted to also use it, and so we made the work to become experiment agnostic. Right now, it's open source. It has a GPL 3+ license. It's hosted on GitHub. It is developed in Python 3, and we are keeping Python 2 compatibility for the current production release, but this is the last. And it's documented. There is an assistant forum. We have workshop every year. We have every second week either a developer meeting or a hackathon that anyone can participate. There is also a consortium as a representing body. So what can you do with DIRAC? There are a few obvious things, like sending jobs to the grid is the most obvious one, and interfacing with different sites. So computing elements, but also the batch systems, in case there is no computing element, and also with the storage element, different types, of course. And then interface with information system, catalogs, message queues, databases, and we are working on authenticating through different identity providers. And a few other things that can be done with DIRAC is managing productions that, these two examples, reconstruction and simulation, are quite typical examples of type of productions that one wants to run in a high energy physics environment, but apparently not only. And managing dataset transfers, removals, or maybe delegate the task of these things to some other tool, like, for example, FTS. There is also a possibility, if properly set up, to have a failover system. So basically, if your jobs want to upload their output to a certain storage element that is down, your jobs will not fail. That's pretty standard, but also we may even have that the whole central services where you have DIRAC installed go down, and if the failover system is properly set up, then you actually will not lose anything. You can also use it for transfer data from the experiment, which is often called the online, to the grid storage element, which is we often call the offline. Okay. This is, again, a bit high energy physics terminology, I think, but okay. And then you can monitor your resources with a policy-based system, and of course there are other possibilities to do. So within the year it has been adopted by several communities, and there are several installations. Now, the two most known ones are here on top left and top right, LHCb and Bell2, but there are many others. Now, what's good is that there are a few installations, not many installations of DIRAC, but those few installations are often used for managing several communities. Now, there is one installation in China with that manage BES3, SEPs. There is one at CERN for CLIC, the linear collider, the future circular collider, I think at least another one, another VO. There's one for CTA, one for Project 8, which I believe is the only one in the United States. Then there are at least two quite large installations. One is at Grid PP in UK, and the other is EGIACE that actually recently joined force with the French DIRAC installation, which was the France Grid installation. And each of these can manage actually, well, I think at EGIACE probably, I don't know, 2 or 3 dozens of virtual organizations community. So that's probably one of the reasons why it is popular. So you can have DIRAC as a service. So basically you can have one installation and deal with each of these. You can manage several virtual organizations, and this is available since a really long time. And this is very good for all those medium, small communities because often they don't have time and especially manpower to dedicate to maintain their own DIRAC installation. Now, I think that a very good way of providing DIRAC as a service is through national initiatives. I think that Grid PP is a perfect example of that, but I think recently also Dutch Grid made an installation. So basically there are a few DIRAC administrators for possibly dozens of communities, and that's okay, save time and manpower. Another reason is that it is feature rich, and with it you can have the workload management, data management, production, dataset management, and the monitoring. And again, this is good for limited manpower communities. There is a tightly integrated DIRAC web app. And the other thing is that, of course, it is very actively developed and maintained. Well, it has always been, actually. The last workshop, someone said that, well, I would say that our users are happy. And DIRAC is said to be stable, and apparently we are doing not too bad as a communicator. A few basics of DIRAC. First of all, the workload management system, because this is, of course, the raison d'etre of DIRAC. So it is a pilot-based workload management system with late binding. DIRAC is known for being the first to introduce the pilots, I think already, well, I think it's at least 15 years ago. So basically the users define and submit the jobs. The jobs have requirements. Job description are stored in the DIRAC job database, and independently there is pilots that are started on the site's worker nodes. They are sent by some pilot factories that we call site directors. And then the pilots, once on the worker nodes, they install themselves. Well, they install DIRAC. DIRAC recognizes what it is the current environment, tries to match the worker nodes capabilities with the job requirements. And then jobs are started on the worker nodes, and there is a continuous feedback. So a big part of what DIRAC does is to start the pilots, and to interact with what we call the computing resources. That is where we can start the pilots. Now, of course, this means first and foremost, well, at least for the For several communities, it means to interact with grid technologies, which means each control computing element and the ARC computing element. But it is also true that there are several communities that don't have access to sites where there is deployed any computing element. So basically, what we do here, what DIRAC does here, is to access through the SSH GSI SSH tunnel, and this is what we call a DIRAC SSH computing element, and then DIRAC can interact directly with the batch system that is there. Lately, it means mostly interactive with Learn, but not only. We have plugins for the various batch systems out there, for example, to interrogate also what is the time left. Also for the virtual machines, there is a virtual machine scheduler, which is that we are recently remade basing it on Apache Deep Cloud, and this starts standard images that are contextualized with at least the DIRAC pilot. And then those pilots that I'm talking about actually can be started in the vacuum, as we say, so they could be started on sites that implement the VAC technology. This was rather popular a few years ago, not anymore, or with Boeing, or there are some examples that are specific to some of the installation. I'm part of LHCb, so I know very well the LHCb part, and I know that in LHCb we are running on the HLT farm just by starting the pilot, as we say, out of the blue, without sending it. And then, of course, there are HPC sites, but which often means that we are using a SSH computing element, then have to interact with Learn, but of course this depends. There is a bit more later on. Just one thing, so there is everything is monitored, of course, regarding the jobs and pilot submission and so on. There is a DIRAC accounting that is a rather historical system that is used for creating the plots that you see on the top right here, but later we are also starting to provide dashboards on Kibana or Grafana. Regarding data management, the basics are those of actually, here we inherited many concepts that were coming actually from early implementation of catalogs like the LFC. Base concept, because at the end there is the single unit in DIRAC is the one of a file, and there is an identifier which is a unique identifier within DIRAC of a file, which is a LFN or logical file name, which is a path, and those LFN can be registered in catalogs, and catalogs are abstract classes, and then there are real implementation of the class of these catalogs. Those LFNs so may have physical file names, which are storage elements, and these storage elements can also be monitored with a policy-based system. And then those PFNs can be accessed during using the several protocols that DIRAC support. Now, regarding catalogs, the DIRAC catalogs are used for implementing namespace functionalities. And you can have several catalogs that live in parallel. So basically, you can say that, right, you do a set replica, a register replica, and that can register that replica on several catalogs, depending on what that means on each of these catalogs. This is very good if one wants to move from one catalog implementation to the other, but not only. DIRAC provides its own catalog, which is the DIRAC file catalog, DFC, which is full replica and metadata catalog, which I believe is used by all DIRAC installation with the only exception of Bed2. And then there are plugins for various other catalogs like the LFC. I think this is not used anymore by anyone, but I might be surprised. There is a plugin for Rusio. There is a plugin for a so-called DIRAC transformation system. And then there are specific plugins that have been developed by the single installations, for LHCb, there is one for the bookkeeping, and I believe that Bed2 still talks to PanDA. Regarding DIRAC plus Rusio, since this was a very awaited feature since quite some time, just to cut story short, since January 2022, Bell2 is using DIRAC and Rusio together. Well, in fact, it interacts with the Rusio file catalog, and they moved Bell2, they moved from LCG file catalog to the Rusio file catalog. Now, there are some developments that have been done and are still being done on both sides, both on DIRAC and Rusio, for the two to interoperate. Regarding the DIRAC part, what's available right now is also the integration of multi-view implementations of DIRAC with multi-view Rusios, and also working without the Rusio configuration file. So DIRAC also provides the possibility, as I said, to manage job productions and data sets management. And to do that, there is a system in DIRAC, which we call the transformation system. I think this is an unfortunately very bad name, but this transformation system is used to automate common tasks related to production activities. And it is a base system for running production, that like data processing production, this can be simulation, merging, data reconstruction, you name it, that end up creating jobs in the workload management system. This is basically a production is the workflow that you want to have. And the data manipulation, transformation, replicates, remove data from storage elements. Basically, a data manipulation transformation ends up creating requests in yet another system of DIRAC, which is called the request management system, which feeds the data management system. Now, all this looks rather complicated and abstract as of now, but I mean, I could make a full tutorial on how all this works, but the transformation system is a really finely tuned system that can manage millions of jobs and files daily. DIRAC also has a web app that is tightly integrated, which is used for monitoring the jobs, the files, the productions, the content of the catalog, and so on. Of course, it is configurable, extendable, and there is a possibility to create dashboards directly inside the web app. And DIRAC can be extended. There is what we call the horizontal extensibility that is for specific requirements. We say that web app is a specific extension of DIRAC, and COB-DIRAC is well, it is yet another way of providing the CLI. Of course, one does not have to have all of these, but yeah. And then each of these projects can be extended in what we call the vertical extensibility for well, communities if they need to have something that is very specific for them. LHV has an extension, for example, that is the LHV DIRAC, and we also have an extension of the web app that is called the LHV web app. Simply because we need to interact with one more catalog, which is the bookkeeping catalog, which is containing very specific information for LHCb, and so we don't have to. We never backported it to DIRAC, and it happens also similar cases for other virtual organizations. Now, I tried to guess why DIRAC is not more popular than what it is. I think it boils down to these issues. The first is that it is rather complex and has a quite high entrance bar. The deployment is something that, admittedly, we have not had time to work much on that. It is somewhat cumbersome. I believe it is known for someone, or at least only for its workload management functionality. We are often a bit late on standards like HTTP services, tokens, and monitoring. Somehow, I think it's considered an HTTP thing and perceived that the design is a bit oldish. So we try to tackle, of course, all these issues that we are aware of, and the others that our user try to push for. So some DIRAC developments, of course, we try to. There are many others, but these are the most those that. The most actual, if you want. We always try to integrate DIRAC workflows in HPCs. We always try to advance on data management, specifically for what is requested by WSCG. We moved to Python 3. We are moving from to HTTP services based on Tornado, and we are moving to integrate token support and the new IDPs like EM and check-in, and provide the Elasticsearch, Kibana, and Grafana dashboards. We also started to take care of the deployment with the goal of providing a Helm chart and running on Kubernetes, and also to use Celery and RabbitMQ and retiring part of the old DIRAC framework. I'll have a slide on HPCs because these are rather hot topic and well, also deserving seminars. There are different solutions that must trade off for different HPCs, and DIRAC, of course, can only take care of the distributed computing issues. Now we have a set of solutions for some of the issues, like running on many core architectures for which there is a so-called pool computing element interfacing with the batch system hosted CERN. This has been largely refactored and improved in the last year, and also to interface with those worker nodes that have limited, if not absent, the network connectivity to the, well, when I say internet, I mean internet connectivity with the, and here we have a new solution that is called push job agent. But anyway, VO actions are often needed. On the software challenges, because of course on HPC you don't always have only x86 architectures, so then the good news is that the Python 3 version of DIRAC clients, and so the DIRAC pilots, can also be installed on the architectures like PPC64 and ARC64. But of course, you still need to be able to start the pilots. Regarding tokens and those two, the current production release depends on bombs. Now, DIRAC V8, which is due in really a few weeks, we have just a little bit late there. It rationalizes many aspects related to the authentication, authorization, token, also support, and so on. We'll also add an experimental support to new identity provider specifically for EM and check-in. And in longer term goals, we want to externalize the users management to those IDPs, because right now the users management is inside DIRAC. We want to use tokens and or proxies for interfacing with computing and storage resources. We very well know how HT Condor is evolving, for example. Regarding accounting and monitoring, I mentioned before that we have an accounting system which is rather historic for DIRAC, and it's also for keeping historic data. This is based on MySQL. And there is DIRAC web app dashboard that can be created based on this data. But we have done lots of progress, in fact, in the last few months to expand on here, and we have now real-time monitoring, and not only which is based on Elasticsearch or OpenSearch backend. And so we can visualize most of the data in Kibana, Grafana, and partially also in the same DIRAC web app. We're also part of some of the communities, of course. We are part of WCG, and mostly, well, LHCb is part of WCG, and LHCb using DIRAC have several of the things that are requested by WCG end up being part of DIRAC itself, and the AGI. So here we need to interface with check-in and also to provide Jupyter notebooks. Just an insight on how many we are. So we are about 6 FTEs core developers. So this changes, unfortunately, rather frequently, and they doesn't contributing developers. We do a lot of tests, certification, and integration process, and we use lots of GitHub actions. We use Jenkins for testing some parts, and every second week we run a certification hackathon. At the end, we end up creating basically 2 releases per year. Well, plus many, well, basically plus patches every week. I also take this opportunity of publicizing the DIRAC user workshop, which is next week, Monday and Tuesday. It is on Zoom. We really tried to go back to live, but not yet. It is for free, but it's not very good for the United States public, because this is in the mornings on the Central European Summer Time. Now, for your info, it's 5:27 here in the PM. But anyway, we record the sessions. If you are interested, if you want to participate, well, register. And if you have questions or comments, I'm very gladly answering them. Here are some of the links for our outreach. In case you have questions, you can ask here or reach us directly. For example, on GitHub discussions, we like a lot.
Thank you very much for your presentation on DIRAC. Are there any questions for Federico? Let me look also in the live notes. So I don't see anything immediate. So something which was curious was you had the slide where you shared the feedback from your user community, which said that communications is one of the killer features. What does this mean exactly? Communications in what aspects?
Well, basically, I think it means that whenever any member of this community asks a question, we answer.
Okay.
Yeah, we often have questions that are even not specifically related to the DIRAC code, but they are related to, I don't know, how do you do a certain thing, or what are the settings of your servers? And well, we always reply.
And related to that slide, which you currently have open, how should I see that DIRAC as a service? So imagine I'm a university group, and can I just go to a website and set up my own DIRAC service, and then I can submit my jobs to let's say one of the grid sites worldwide?
Well, often what happens is that I'll take the example of GridPP. Okay, GridPP is an installation of DIRAC. It's handled by well, 3 people part-time in UK, and they have, I think, 20 communities. And out of these 20 communities, they are saying that most of them are very few people. Sometimes really, yes, university groups, and they just ask, can I use your DIRAC for submitting to the grid, whatever it is. Now, as we know, there are some grid resources out there that allow anyone to, that they don't have any pledge, but they allow anyone to get in. And so as long as there is an agreement, it's all right. But yeah, and not most of the, I mean, anyway, one has to be in VOMs at the moment.
Okay. And
at
then,
the moment, yes.
And then we have one raised hand. Please go ahead.
Hello. Just curious how tightly integrated Rusio is. Is it just made minimally interfaced as it was an LFC, or do you use the features of datasets and containers from Rusio, replacing those functionality from DIRAC?
So it has to be said that the belt-shoe integration of DIRAC and Rusio has been done within the belt-shoe DIRAC extension. Then lately we have added an integration of DIRAC with Rusio that is, let's say, for everyone. It is inside vanilla DIRAC, and it is based on the needs of the developer of that, which is basically, in this case, is also GridPP. The base part of, let's say, using the Rusio file catalog as a plugin are there and are maintained. Regarding then there is a few more issues that have been solved here. There are a few more topics that have been added. For example, there is an added synchronization between what is the view of DIRAC, of the grid of DIRAC, and the view of the grid, well, most of the view of the storage elements that is in Russia. Regarding the data sets management, the concepts that are within DIRAC and the concept and Russia are rather different. So the answer to the question is mostly no, there is not a one-to-one relationship. I don't know if that is enough as an answer.
Thank you. Thank you.
Last chance. Oh, Paul, please go ahead, Paul.
Thanks for the talk, Federico. It's really nice. I've got a kind of high level question. So I was curious, were you, so in terms of opening DIRAC up to other experiments and other communities, do you think that has been a net benefit for LHCb as well?
I think by now I would say yes. If you would have asked me this question 7-8 years ago, I would have said probably no. But now I think that the community of developer is now mature enough that yes, definitely LHCb has profited out of the work of that other communities ended up putting in DIRAC.
Great, thanks a lot.
Thank you very much for your presentation. This was very interesting and a really good update on what is happening with DIRAC. So thank you very much, Federico. Now we go in alphabetical order through the workflow and workload management systems, and next we hear about PanDA from Tadashi Maeno.
Yes, so I'm going to share my screen.
Yes, please.
Okay, so let's start my video. Okay, so I will talk about PanDA evolution for Atlas and beyond. PanDA stands for Production and Distributed Analysis System. So it is a workload management system. It managed for 24/7 processing on roughly 800,000 concurrent cores globally for Atlas. It supports all Atlas workload from event generation to analysis with all resource types available for Atlas. There are roughly 150 competing sites. Computing centers and 1,500 users. It runs 300 million jobs per year in tandem with Lucio for data management. It has a smooth horizontal scaling, and it provides easy user client tools. And it has a highly developed monitoring and historical data reporting. And recently, it had a support for Postgres database backend and edge community-based service deployment, and some development related to a Google project. And also, it has a Jupyter notebook support and token authentication. And IDDS is a new software product which works with together with PanDA. IDDS stands for the ID Intelligent Data Delivery Service. It is a joint project between Atlas and IRISEP, and it supports arbitrarily complex fine-grained workflows defined via DAGs or workflow or description languages. Before going through my presentation, I just want to clarify some terminology like workflow, task, and job, because those words could be used in different meanings in other systems, and I want to confuse. I want to avoid the confusion. There are hierarchical workload entities in PanDA. So workflow is the top level or entity of workload to accomplish a scientific objective. And there are multiple steps in a single workflow, and each step is mapped to a task. So this means a task is a group of tasks. Our workflow is a group of tasks. And generally, a task process input to produce output. Input is a collection of something. Something means it can be a collection of files, a collection of parameter set, or a collection of random seeds, and things like that. And it is possible to have a primary input in addition to multiple secondary input. A job is an artificial partition in a task. A task is composed of multiple jobs. Jobs takes process a subset of input or computing resources to produce a subset of output. So on the traditional grid, a job ultimately corresponds to a batch job in the batch system. And there is an optional entity that is event. Event is a minimal unit in each constituent of input with the finest processing granularity. Okay, let's move on to evolutions for Atlas. PanDA was born in 2005 and has been working for Atlas since then. And Atlas has an open organizational culture which encourages innovative evolutions in PanDA. While the system has been steadily running for high volume Monte Carlo production and data reprocessing, and making large-scale computing resources available for the individual users. PanDA has a strong capability to integrate heterogeneous and global resources such as the grid, high-level trigger farm, HPC's commercial cloud, volunteer computing, and GPUs. And also, it has a capability to manage workload with various granularities. This picture shows the timeline for our LHC and a high LHC. So there was a long shutdown recently. So this long shutdown provided a great opportunity to develop a lot of R&D activities for Lancy and high-level LHC. So the main goals were automation and optimization of resource usage and support for new workflows. So I will highlight major evolution in next slide. So the first thing is integration of emerging resources. PanDA has various plugins to access resources. It is based on HTTP ARC middleware, or some of them use low-level batch system API like Through and PBS, and some use Kubernetes API, and also it is possible to use RPC over SSH. And the deployment model for the for the resource manager is quite flexible. So it can run as a central service or a regional service, or even it can run on edge services on some restricted resources like HPCs. This picture shows a significant contribution from Euro HPC systems like Vega. And the bottom picture shows Parsl MC production exercise on Google Compute platform is various VM types, where you can see the VM types was dynamically changed from on-demand to spot instance through preemptible, and the system worked very well. Next thing is data carousel. Data carousel is fine-grained disk-efficient data staging. This is the first use case of IDDS in production. So it works as IDDS works as a high-level service to orchestrate PanDA and Lucio to create disk replicas on demand and delete those replicas aggressively as soon as processing is done. So we can use disk resources more efficiently. This is a great achievement of IDS because it is mitigating the disk problem that is the most crucial issue in Atlas. We are still on Atlas, but I switch the topic to new and evolving workflows. Currently, which are currently applied to Atlas, but they are not limited to Atlas. The first thing is a hyperparameter optimization service. You might be baffled because this is completely different from traditional help topics, but probably you may need some sort of flexibility or conceptual jump to digest, but I will try to explain. So anyway, so in the traditional help context, input for processing is a files, and the contents of the files are event. So, but from PanDA's point of view, they are just logical entities, and they don't have to be physical files or event. So for HPO or workflow, input is domain space, and their contents are hyperparameter samples, and they can sim and those objects can seamlessly be mapped to the hierarchical workload entities in PanDA. For example, hyperparameter sample is mapped to event, and they can be managed well with the capability to manage workload at the sub input level. So for each hyperparameter sample, the system calculates the loss, and the loss values are passed used to define the domain space for the next iteration, and this workflow loops over, and this is works quite nicely. So and concerning the payload, there is an interest payload. And that is an elastic distributed training on Amazon EKS. So the idea is to run advanced distributed machine learning training with Horobot on multiple GPUs. And the key trick here is the system spins up hybrid clusters on Amazon EKS. So where Headbot runs on demand GPU only instances, while Workabot runs on spot GPU instances. So generally, GPU resources are quite expensive, but we can save the money if we use a spot instance. But the main problem here is the cluster size can be dynamically changed. For this, so we need a Horobot. And for this kind of complicated payload, the PanDA's capability for complex resource provisioning is useful. Segmented hyperparameter optimization. In a traditional hyperparameter optimization, there is only one machine learning model for a monolithic object. While but in some cases, objects can be logically segmented. For example, this puppet could be segmented into arms and head and body. So of course, it depends on the nature of the object and use case. So the segmented HPO is a HPO service for a segmented object, where you can define one machine learning model for each segment, and a single HPO session can optimize all machine learning models in one go. So for each model, we can expect a smaller training data set for each model. So this means we can have faster turnaround, and trainings can run in parallel. So this means that this workload can be distributed more. One concrete example in Atlas is a fast Carga, where there are 300 networks in Atlas detector. So 100 ether threads times 3 particle types. So that is a proton, electron, and pion. So on 100 GPU days requires to train 300 guns. So it will be better to be parallelized. And in this for fast Carga, one network corresponds to one segment. And also it is enough to have one segmented HPU session instead of 300 individual sessions. So this picture shows what actually happened internally, but I don't explain all the detail. But and you might find this is too complicated, but this is actually used to converge fast Galois parameters and full detector training for central production in run 3 for Atlas. And there is a variant of HPO workflow. That is MC toys based confidence limit calculation with IDDS. As you know, confidence limits are quite important for physics analysis. And this workflow is composed of independent MC toy calculations and post-processing to extract limit. So under these steps can be nicely mapped to HPO or workflow. So essentially, this is implemented as a HPO workflow without any iteration. Okay, running workflow. In PanDA, using PanDA, users can run complex workflows with conditional branching, nested workflows, parallelization with scatter and loops. And the user can leverage PanDA's capability to integrate heterogeneous resources and workloads. For example, a user can do something like this picture. So first, the user can train machine learning model on a multi-GPU cluster. Then this machine learning model is passed to the grid to do the mass production, and the production and the file product passed to the final analysis, and they can run different resources. This picture shows some workflow example, like for example, conditional workflow and loops, and loop can be parallelized using scatter. So it's parallelization for horizontal parallelization, and this is vertical parallelization. So as you can see, this user can define quite complicated workflow if necessary. One of the use case which requires a complicated workflow is active learning. The idea of active learning is to improve analysis efficiencies by using the definition of the search space for the next iteration based on the result in the previous iteration. For example, the goal, the goal is to find this truth. Then you could do calculation in the broader band, and then in the first iteration, then check the result, and you will find a good result here. Then do the calculation in a narrower band in the second iteration. So in this case, you can exclude those regions because they are hopeless. So we can expect the reduction of total amount of computation. And in active learning, we use various machine learning optimization functions and techniques to define the search space. This picture shows what happens for active learning workflow for mono HBB analysis. First, you have original parameter space, and you could take several parameter points. And for each parameter point, you run a full production chain to produce derived analysis data object data file and root interpol for each point. And they are passed to recast step to calculate confidence limit, and all confidence limit are used to define a new parameter space. And then this workflow loops over. And one point is, so you can run this Liana recast step on Liana. So this means users can have a complex workflows which are offloading sub workflows to external automation systems like Liana, Airflow, or Luigi. And actually, the PanDA has a capability to send secret information to the payload, and it can receive a callback from external systems to work to have a synchronization with external systems. Okay, pseudo interactive analysis. Interactivity is one of the hot topic in Atlas. And sometimes the people start talking about Jupyter or something like user interface like Jupyter for interactivity. But interactivity is an issue more for process backend rather than user interface. For example, you don't feel any interactivity if you have a synchronous user interface and slow backend. So the idea of the interactive analysis system is to construct an interactive system on top of asynchronous resources. So that have interactive user interface, but we on top of geographically distributed analysis process backend, and that should provide some reasonable or responsiveness. So for express analysis, we could use some bulk spin-up with Kubernetes on commercial cloud resources rather than traditional grid resources. But generally, users can accept longer response time, depending on data volume, intensity of computation, and their expectation. There is some advantage in this idea. So because we can provide central accounting and fair share one-stop service isolating users from various process backend. And we can expect a further scale up with more competing resources across various resource providers. But there are some advantage. Clearly, latency will be the issue. And also we need more development effort for interface and monitoring. Because of lack of direct access to competing resources. This picture shows the difference between a traditional interactive analysis and the interactive analysis. The key point here is that for traditional interactive analysis, you still have all resources locally, while through the interactive analysis, the resource can be globally distributed. In any case, there are some ongoing efforts to get rid of the latency from the entire system, and we are going to demonstrate rapid resource provisioning. So, concerning the current status of our R&D activities, so resource integration, data carousel, HPO, and workflow support are all in production. But for HPO, there are still room to improve user interface and monitoring. And the number of users is still limited. So we try to attract more users once as machine learning becomes popular in Atlas and HEP. And for workflow support, this is being improved with the active learning exercise. And integration of external service and pseudo interactive analysis are still ongoing activities. And we expect more activity to come. For example, we are writing a proposal to generalize scale-up machine learning services beyond Atlas. Okay, I'll move on to PanDA for Ruby. So the mission of Ruby is to conduct the 10-year legacy survey of space and times. And Ruby has a handful sites. They are in US, in Google, and UK, and France. And they are going to produce a billion files per year, and they run 200,000 short jobs in parallel. And for user analysis, they have a Jupyter-based Ruby science platform. And for data production, they use PanDA. PanDA has integrated into their system in the first half of last year. And after commissioning and evaluation, the Ruby finally decided to adopt PanDA. So this means it began as a demonstrator, and now it is for production. Ruby requires DAG-based processing. Actually, DAG support in PanDA was originally developed for Ruby. And the system is quite stable since last October. And this brought us a new PanDA hire for Ruby. One of the important interesting development for Ruby is a cozy real-time log access. The main idea is to watch the tail of the payload log, and when it's changed, it adds job information and sends as JSON to external logging service like Logstash, FriendD, and Google Cloud logging. And preliminary implementation for this mechanism is already available, and the Ruby has been used this mechanism in production since last fall. And this is being refactored to be experiment agnostic because there is strong interest from Atlas. Concerning PanDA service for Ruby, currently Ruby are using DOMA PanDA service, PanDA instances, which are maintained at CERN. And this is a kind of a playground for non-Atlas experiment to try PanDA. And this they are going to install PanDA service at the Slack. So this means there will be PanDA instances at Slack which are dedicated for Ruby. Okay, then move on to PanDA for SPHENIX. SPHENIX is a new detector under construction for the facility at BNM. And SPHENIX has a very small software core group, and the timeline is quite tight. So they decide to use existing tools like PanDA and Lucio. Actually, SPHENIX adopted PanDA at about the same time and with the same timeline as Ruby. And SPHENIX used DOMA PanDA instances at CERN for evaluation and pre-production. And SPHENIX and Ruby have very similar needs for PanDA service deployment. They use Postgres SQL, Postgres backend, and Kubernetes and OKD based deployment of services. And one main difference from Ruby is SPHENIX use Lucio from the beginning. So they are leveraging years of PanDA's experience with Lucio and Lucio expertise at BNL. And both SPHENIX and Ruby want to have their PanDA home-based PanDA services up and running at BNL for SPHENIX and at Slack for Ruby. This is a SPHENIX handy remote execution coordinator. Is a production system for SPHENIX, which is built on top of PanDA and Lucio, and the workflow is described in DIRAC and common workflow language. Okay, conclusions. LC long shutdown 2 provided a great opportunity to develop a lot of R&D activity in Atlas PanDA for Run 3 and High-Level LC. The main goals were automation, optimization of resource usage, and support for new workflows. And that revealed PanDA's capability to manage emerging workload, as well as a traditional app workload. And some activities are still ongoing, and more challenge will come. And PanDA has been expanded to Ruby and SPHENIX beyond Atlas, and experiment agnostic PanDA services and deployment with Postgres backend and container plus Kubernetes are reducing the difficulties to adopt PanDA. But each experiment doesn't have to take all advanced function in PanDA. That totally depends on requirement or needs of each experiment. But we already see some nice synergy between the effort, efficient and mutually supportive. That's all.
Thank you very much. This was a very interesting talk with a lot of information. The first question is from Doug. Please go ahead.
Yeah, I noticed that Apptainer, which is the new name for Singularity, is talking about releasing checkpointing. So have you thought about in the PanDA team what it would take if we had checkpointable
checkpoint on the payload, you mean?
Yeah, exactly.
Actually, there is some, I believe, early idea to use checkpointing, but probably we need to revisit. But if the payload is support checkpointing, we are happy to support as well.
The next question is from Michelle.
Yes, hi. I have the curiosity that it was mentioned the integration with Jupyter, and also in the slide 20 is mentioned how it's used with the traditional interactive analysis, not the synchronous one, but the asynchronous. I would like to know how it works, the user interface via Jupyter to submit the jobs. Is this something that is enabled via just a prompt on top of the Jupyter Hub, or has some other interface additional?
So in Jupyter Notebook, you can just need install PanDA client. And then from this, you can submit task from your own notebook. So because and we already support OIDC tokens, so you don't need to install grid middleware.
I see. So it's mostly authentication and then authentication enable and then the submission directly from the notebook.
Right.
Okay, I see. Thanks.
David.
Yeah, so very nice. One of the things back on your slide 11, and I think you may have addressed it after, but I'm not sure I fully caught it because there was so much information here. It was very nice. But one of the things I didn't quite get on when you're breaking up and doing the parameterization on the different sections of ADA and PIDs, how do you make sure that when you bring it all together that there's no discontinuities between those boundaries that the individual GANs were trained on?
Actually, it must be guaranteed on the payload side. So from PanDA's point of view, they are completely independent and there is no interaction.
Okay, so it depends on, they'd have to smooth that out
right
on the other side. Okay, thanks.
Right.
I have two questions myself. So you spoke at the beginning about your intelligence data delivery system, and then you later on talked about active learning. Is this active learning your intelligent data delivery system, or are these two different things?
Actually, let's think. Okay. Actually, intelligent IDBS orchestrate PanDA and other components like Liana and Kubernetes. So it works as a high-level service to run active learning workflow on PanDA. Did I answer your question?
Well, and then this active learning is part of that high-level orchestrations via your
right.
Okay.
Yeah,
okay.
Yeah. Mm-hmm.
This was my question, just to understand the connections.
Mm-hmm.
And the other question I have is about the adoption in Atlas. So you mentioned this is the standard system in Atlas since 2005. If I remember correctly, then Atlas had first collisions in 2009, and you have a user base of 1,500 people. But when you started before 2005, what has been used and how easy was the adoption of the system in the collaboration?
Right now, first, this PanDA service was at BNL. First thing we have to do is to migrate this system into CERN. And the first we are using MySQL, but CERN has Oracle infrastructure, so they asked me to migrate to Oracle. So it was a kind of challenge, but I think it takes about a couple of months to migrate from MySQL to Oracle. It was not very easy, but we managed to do that.
But from the you answered my question, but I was aiming more for the user experience. So the many people in Atlas who do their analysis, and I think in 2005 they already worked quite a lot on simulated analysis. Was this straightforward?
My problem, no, sorry. So in any case, we had to educate people because only people used to use the local resource and do some intermediate. Yeah, I think there is some jump was required.
Okay. Thank you very much.
If I may just chime in, as a user, as one of those users, I think people in Atlas mostly never knew anything else but PanDA. There were a few early adopters and maybe were submitting directly. Great job with Lightning WMS or using things like Ganga, but very few. So it, to most people, to all the tutorial, it's always been PanDA.
Okay.
Everything was converged.
Yeah. No, I mean, user base of 1,500 people is quite impressive. All right. Are there last chance for some questions for Tadashi? Then thank you very much again. This was an enormous amount of information, and we covered today 3 workflow and workload management systems, and we were going in alphabetical order. So the third, last but not least, is Parsl, and the speaker will be Chard from the University of Chicago.
Awesome, thanks. Oh, can you hear me, Marcus?
Yeah, very well.
Wonderful. Thank you. Let me just share my screen and hope for the best. Okay, can you see my screen?
Now, yes, now we have it full screen. Thank you very much.
Awesome. Okay, well, thank you for the invite to come and speak to everyone. So I'm Chard, I'm at UChicago and also on Argonne National Lab, and I'm presenting here, of course, on behalf of a large group of people, some of whom I've listed here. So I thought I'd start with a couple of examples of the types of workflow. I mean, workflow is a particularly loaded term because it sort of means everything and nothing at the same time. So I think it's important to sort of try and characterize what type of workflow, what type of workloads you're really focused on. So I've got a couple of examples here. So the first is an example from the cosmology space, a group of researchers as part of the Dark Energy Science Collaboration, which is one of the, it's probably the largest science collaboration associated with Rubin. And they've been using Parsl for the last few years for sort of various analyses and also for some of their image simulation and image processing requirements. So this example is a big initiative they ran over the last couple of years, essentially to simulate data that's likely to come out of Rubin so that they can build downstream analysis pipelines. And as part of this work, effectively what they did is they took these large catalogs of things in the sky, they ran them through some image simulation code, they parallelized it across large supercomputers. So you see down the bottom there, Theta and Cori, where they were running it basically the entire system sort of scale. They were using containers where they had their packaged image simulation code, and they used Parsl effectively as a bag of task executor. So they wrote a Python script that could churn through all these catalogs of interesting things, allocate these bundles of compute tasks in the Singularity containers running on the large supercomputers to create these different visualizations, where each of the simulations was trying to basically replicate what each one of the sensors would produce. So that's sort of your traditional bag of tasks type workload. And you'll be surprised actually how many users use workflow systems really as just a simple abstraction for executing a bag of tasks. The second example is more of a DAG-like workflow structure. So during the initial stages of the COVID pandemic, everyone probably saw that the DOE assembled a large group of people to start looking at anything they could do to try and help out. And we were involved in the NVBL effort here to try and screen small molecules to see which ones might be potentially good candidates as therapeutics. So as part of that process, we used Parsl in the early parts of the workflow. Of course, there were hundreds of people involved in this, so it's a small slice of what was going on completely. But we essentially screened roughly 4 billion molecules. We canonicalized them. We computed features of them. We computed fingerprints, images, etc. Passed them through machine learning and similarity search type algorithms to try and identify potential therapeutics. And for this, we had more resources. This is an interesting scenario. We had more resources given to our group than we had the ability to use. So we were using systems all across the US and around the world to run this type of processing. So just a quick motivation of why we built Parsl. So our group's been building workflows for 20 plus years, or workflow systems, originally with the Swift workflow language that people may be familiar with in the early 2000s. And we looked probably about 5 years ago thinking, well, we've got an opportunity to rethink how we want to attack the workflow space. And as part of that effort, we rewrote Swift into this new workflow library called Parsl. So a few observations. I don't think this is new to anyone. Of course, parallel distributed computing's here to stay. I think we increasingly see sort of researchers from all walks of life now needing to use parallel and distributed computing systems, in part because Moore's law slowing, in part because data size is getting bigger, in part because workloads are becoming larger with things like machine learning codes, etc. The second thing we observed is that a lot of software now really is assembled rather than written. So often people piece together components that already exist in different languages. You see this in machine learning, where effectively people have like a Python interface and they've got lots of different components that are running under the covers. So this whole notion of using a high-level language to integrate and wrap components to orchestrate them in a productive sort of manner. And the third thing we observed is that, and again, no surprise, I don't think I'm surprising anyone with these points, is that Python is really pervasive. So in our science world, I think most researchers are very comfortable with Python. Most are using it at some level, and it's really taken over. And I think in part it's because of the sort of productive focus. I think it's also in part because of the ecosystem that exists around it, the SciPy libraries, Jupyter, et cetera, et cetera. And so we sort of looked at that, and the Swift language was actually a domain-specific language for creating workflows. And we, after 10 years of experience with that, we sort of found that, well, many researchers, rightly probably, are unwilling to really adopt a new language for representing their workflow. What they'd like to do is work in an environment they're already accustomed to. The second thing we looked at was sort of more of a static declarative type approach for defining workflows. And from what we could see looking around is effectively everyone starts with the best intentions. Let's define a very simple specification for my workflow. But very quickly, people start to say, well, now I need some branching. I need some conditional logic. And eventually these like JSON or XML-based descriptions become XML, JSON plus some random programming language of your choice jammed into XML tags or whatever. And it becomes basically a domain-specific language very quickly. So we thought, well, why don't we invert this? Let's start with a language that everyone knows, and let's try and add workflow constructs to it to try and represent the types of programs that we were seeing in our user community. Because I'll if I go over time, just let me know. So in a one slide sort of description, what is Parsl? Parsl is a parallel programming library for Python, where we have some basic workflow constructs that allow us to create these DAGs and execute them. Where possible, we've tried to leverage things that exist. So we've built on the concurrent futures library in Python and the concept of futures as a way of connecting and assembling these DAGs in a Python program. We introduce a couple of new constructs. So these app decorators that really are ways of telling the Parsl engine what pieces need to be linked together, what pieces can be run concurrently, etc. So we have a Python app that, as you would imagine, wraps a pure Python piece of code, and then a bash app that wraps anything else. So that's for calling a command line invocation, a binary, etc., something in another language, which of course, if we're thinking about orchestrating different things, that's important. So the basic model sort of works in a concurrent DAG-like model where we assemble this data flow. We think that's a nice way of representing parallel programming. And then we're focused a lot on the back end side, the runtime, so that we can make these scripts independent of where they run. So by using a Python configuration, you can change if you're running on your laptop or a supercomputer or a cloud or a cluster, et cetera, of different types. One great thing of Python being Parsl being entirely Python is that we can use things like binders. You can click that link at the bottom there and run through our tutorials. The entire code base is written in Python. It's really designed for Python in Python. So as I said before, we think this data flow model provides a really intuitive way of assembling parallel programs, because effectively what you're doing is building up this DAG, directed acyclic graph, of data flowing between these invocations. And so we've found from working with hundreds, maybe more, of researchers that this sort of resonates in terms of how they understand the types of analyses they'd like to be able to build. The data flow model works in two ways. It sort of works natively with Python objects, or any sort of Python data being passed between these apps, and also with files, where files can be sort of local if you're running on a large cluster, or they can be accessible via HTTP or FTP, or they can be movable via Globus. We actually also have SCP and some other things in there as well, but those are the main data transfer mechanisms that are used. So I thought now we'd run through a quick example, sort of what does this look like in practice? I showed you sort of some pretty pictures before, and now an example. So this is a typical sort of workflow example, the Modus example. You have some satellite imagery coming in, you want to process it with a few steps and produce some interesting maps at the end of it. So if we have this sort of DAG structure here, where we have an almost MapReduce structure actually with various apps, the first thing you do when you're creating a Parsl program is you effectively you go and wrap the pieces of your workflow. So in this case, we've got a bash app there where we're calling a shell script, land use, and we're passing in an input image and we're specifying what the output files are going to be produced. And then we might have a couple of Python apps here where we're passing again in the image and saying how many chunks we'd like it chunked into, and an analyze package, which is that reduce stage that's taking as input the land chunks from that first app and the colored chunks from that second app. So this is obviously simplified for the purpose of this presentation, but you can imagine how this would look. Often you'd have a simulation script, or you'd have a Python package in another module that you'd call with some parameters, and you'd just basically wrap that with these deck arrays to make them accessible. And then the next thing you do is then call this code using standard Python syntax. So essentially here, we've got a for loop, we can have branches in it. The first thing we're doing is we're running a bunch of chunks, running over a range of input data. We're calling this land use app, which is just a function call with the image input. And we're saying for each one, produce a unique file output, just indexed by number. We append that to a list. The second thing we're doing is then running that colored app, which is in this case, just one call to it, where we're saying run the image and produce 5 chunks. And the important thing here, you see no synchronization, right? We're just running these things because we're using this future library. Futures are coming back again, but the processing is not necessarily happening immediately. That's going off and running. And then the third thing we're doing is calling the analyze app, which is that reduce phase, where we're passing in the L chunks, the list of chunks from the land use app and the colored future. And so Parsl here will understand that this is an invocation that's taking futures as input. And so Parsl will basically know to wait until those futures are resolved before actually executing that analyze app. So that's sort of your canonical way of using Parsl. There's some pictures, some arrows to show where the data flow is happening between the outputs from the first app and the outputs of the second app. So how does this sort of work in practice? So this is a snippet taken from our binder tutorial, computing pi in a Monte Carlo sort of model. But what basically happens is you have your Python script. It can be written in a Jupyter notebook. It can be written in Python. As that's running, Parsl is intercepting these calls to the apps and starting to assemble a DAG. So as we saw before, when we called land use and colored, we're basically throwing it into a DAG. Parsl then has different connectors for how it wants to run those apps. We have a couple of abstractions there that I'll speak about in a minute. But essentially, if there's resources connected, Parsl will start firing those apps down for execution. We use a dynamic model, so we start running things immediately. There's no sort of pre-compiled DAG. It's sort of a DAG that's assembled over time. As those results come back again, we might start filling in more of the DAG. And of course, as soon as those tasks are ready to be executed, they'll be sent down for execution on the connected resources. So I mentioned before that we have a couple of levels of abstraction. The first is this abstraction to speak to different types of resources, where a resource might be your local PC, it might be a grid, it might be a cloud, it might be a supercomputer. So for this, we created our own abstraction called a provider. It's a very simple abstraction. It basically is for deploying pilots or deploying our worker software on nodes to run. And so we have wrappers for a dozen or so different systems or different scheduler or interface types, anything from Slurm to PBS to Cobalt to clouds like Amazon and Azure, and to local execution where you fork a process. So you see there on the right some random configurations for different systems in which we're running, and all of this is in our docs, but essentially this is just a Python configuration of the type of resource you want to use and how you want to use it. I thought I had a different slide here, but we'll go into, this should have been one slide later, that's right. So the way this works, originally we started with a very sort of vanilla JSON-based config, and we decided we'd completely embrace the Python sort of model. The advantage being if we specify our configs in Python, we can do things like tab completion, and we can have IDE integration, et cetera, et cetera. You sort of are bound to the rules of that configuration in the standard Python way of doing it. So we see here we're declaring two configurations, using the first using local threads on your local machine, and the second using a Slurm resource, in this case Cori at NERSC. And then in my code, I can basically import these different configs depending on what I want to do. So I can define an environment variable, I can hard code the config I want to use, I could make it a command line arg, etc. I can do whatever I like to be able to pick and choose these configs. And we've even seen people dynamically produce these configs in their execution script. So the second thing I wanted to mention was that the second abstraction is our executor abstraction. And so the provider abstraction is really about speaking to different resources. The executor abstraction is about defining how the tasks are going to be executed. So when we initially built Parsl, we actually used we looked around at what sort of interfaces there were, because the interface again is quite simple. Given us a list of tasks, execute the things and give me back some pointer where I can control them. So to do so, we adopted Python's concurrent futures executor interface, which is a standard Python interface. We used the IPyParallel executor to start with, because that worked very well for various settings, and that got us a fair way. But we got to the point where we needed to expand, customize some of that functionality. So what we did was we built 3 of our own executors, focusing on the first one, high throughput, which works to modest scale of a few thousand nodes with 64 cores per node, so on the order of 60,000 concurrent workers. We built an extreme scale executor that works on MPI, and a low latency executor for tasks that really can't go through some of that overhead, so you want responses very quickly. In practice, 99.9% of our users use the high throughput executor because it's sort of a nice middle ground. It provides fault tolerance, monitoring, et cetera, and it works to fairly large scale, really. I mean, if you're running at 2,000 nodes with 64 cores per node and each one running an individual task, that's actually fairly high concurrency. The thing that we've been surprised about that I think has been great has been that by picking the standard interface, we've actually been able to interface with other systems that basically implement their own pilot job models. So examples down the bottom here, WorkQ, build out of Notre Dame, Radical Cyber Tools that's built out of Brookhaven, Flux that's built out of Livermore. We've been able to plug these systems or these pilot executors into the Parsl framework very easily, to the point now where WorkQ is actually starting to overtake HTX as our most popular executor. So the desk guys, as part of the LSST Rubin group, they're actually using WorkQ now as their chosen executor. And to be able to plug that in is just a change in that Python configuration that you saw before. So you can effectively change this this executor from high throughput executor to the WorkQ executor and pass through the parameters that need to be passed to WorkQ to run things. Okay, so we're starting to run a bit short of time. We come from a CS world, so we've done a lot of scaling analysis. This is a paper we wrote 3 years ago now, it would seem, where we analyzed the scaling performance of our HTX and XX executors against other well-known, primarily Python-based models, so IPyParallel, Dask, Fireworks, etc. You see there we're seeing relatively good scaling up to a point, but we see at least no limitations up to using the entire supercomputer. In this case, we did this on Blue Waters, so we weren't using the entire supercomputer, but we were using up to 8,000 nodes to run, where we were running individual tasks on individual cores on those nodes. And of course, we try and shape this as a worst case. We're running very short running tasks. You can see there we're running in strong scaling 50,000 1-second tasks, and for weak scaling 10 1-second tasks. We also ran even shorter tasks, but of course, that basically at that level, you're just analyzing overhead. And in practice, when you're running much longer tasks, minutes or longer, then scaling performance is even better. But I think the highlights there really are that we were able to basically fill these nodes, fill these workers up to a fairly large number. We stopped as we ran out of allocation. Surprisingly, people don't like their supercomputers being used to run a number of sleep tasks, but it informed a lot of the work that's gone on since then. So I gave you a snippet of a couple of applications at the beginning. We run a yearly user meeting called Parsl Fest. So on that website there, you can see the last 3 years, a bunch of talks from interesting scientists that are using Parsl, on average around 20, 25 talks every year. These workflows really span everything from biology to social sciences to material science. We've worked with some people doing education as part of QuarkNet to install or to build little HEP cosmic ray analyses things in their classroom, and then they use some Parsl for some of the Jupyter-based analyses after obtaining their data. The other thing I wanted to point out is that Parsl is an open source community, so the code is completely open. The community is very open. This was a photo of our first Parsl Fest meeting when we were in person. Of course, the last two have been virtual. Our group of contributors is growing, so we're up to 60 odd contributors that are contributing in many ways, from code to documentation to tutorials and other things. So that's the end of Parsl. I have two more things I wanted to mention just in this talk, given the opportunity and the focus. So the first is a relatively new project. It's been funded by NSF for about 2 years now, called FunkX. And this grew out of this common Parsl use case where people came and said, I want to be able to run computation from the comfort of my own home on my laptop on a remote cluster cloud supercomputer. I wanted to be able to use more than one of them at one time. And so we built support for this. I think most workflow systems have support for remote execution of tasks. We built it using SSH. And SSH, of course, comes with a bunch of challenges, from getting users to configure keys, getting users to configure port forwarding, et cetera, and the fragility of those SSH connections. It's not a great story to sort of say, well, you can use SSH, but keep your laptop on the entire time that job's running, sort of thing. So what we looked at was building a new system that was essentially Parsl as a service. So working with the Globus team, of which I'm a member, we looked at the success of the Globus service, which is basically a cloud-hosted managed data transfer or data management service. And we thought, how could we adapt that model to cloud-hosted managed computation using the Parsl model for how we can actually speak to the resources and run a number of tasks. And so with that, we've built the service. It's accessible. It's called funkex. It's on funkex.org. You can basically pip install the client library and the endpoint library and be able to start running tasks remotely. We've run this to fairly large scale. Over the last few weeks, I've been running screening of 180 billion molecules for stability. I did it in relatively big chunks, but still would have run on the order of 100,000 or more tasks to actually do that. The way the system works is, as I said, you can think of it like Globus. So there's the funkex service in the sky that's hosted and run by us on Amazon. It presents a REST API. It also, which allows people to register functions and then execute those functions. The advantage of running it is that cloud-hosted services allows users to outsource the annoying stuff, the being able to connect to the endpoint, the being able to retry when the endpoint goes offline, the being able to catch errors, et cetera, et cetera. And so we think this provides fire and forget execution, where you can basically just say, run this 10,000 tasks on these two endpoints, turn your computer off, come back in a week and retrieve the results. The second part to the architecture is the endpoint software. And so this is sort of like a Globus Connect Personal, if people know what Globus is, except it's a pip installable agent that you can just install on your machine, configure it using that same Python configuration syntax I showed you above with Parsl, and you can configure it to basically execute like with 3 cores on your local machine, or you can configure it to execute with 1,000 nodes on a supercomputer. Exactly how Parsl does things. You can configure it to use containers, etc. This endpoint dials out to the funkex service in the sky, so no need for complicated firewall rules, and will retrieve workload, run them, and send the results back to funkex. Funkex keeps the results in the cloud for, I think, about 2 weeks before users have to retrieve them. And then there's the SDK component, which is a Python library for being able to submit tasks. We also implement that same executor interface. You can use futures. You can just execute a bunch of tasks with the executor telling us which endpoint to run it on, and then you can retrieve those results immediately if they come back quickly or at a later time. We think this is cool because you can really route execution wherever you would like, to where data might be resident, to where you might have an allocation, where you might have the best type of resources for that execution, et cetera, et cetera. We're doing a lot of work actually on edge computing here, where people are running functions at the edge on sensor networks, et cetera, for different types of computation. So I'm just going to go out of order. I also added one more thing. Actually, no, I'll finish this and I'll do the other thing. So just a quick summary of Parsl. So as I said, pure Python model. We think that it provides a productive way of implementing workflows, where workflows mean anything from bag of tasks to DAGs. We think it provides a deterministic model. We've shown it to be relatively scalable and portable. We're running in a bunch of different clusters and supercomputers. And we think that it provides a fairly flexible model. So you can build up these workflows from random bits of code in different languages through to Python, parallelized Python scripts, through to glue things together and connect them into workflows. So the final thing I wanted to mention just briefly is we're also involved in the ExaWorks project, which is ECP, the Exascale Computing Project, workflows project. The idea of this project, and I thought it would be interesting given many people here are from the labs, I thought it might be interesting. So this is an open project. It's community-based, where we're trying to support workflows in the DOE ecosystem. And when I say sort of support workflows, we're taking this fairly broadly, from users of workflows to developers of workflows like myself, to the facilities that are really integral for being the middle person between the workflow system and the user in many cases, and even the vendors as part of the new procurements that are going through. There is sort of two real main focuses. The first is there's some technical work where we're trying to build an open SDK of workflow components. So we're trying to take that Parsl type model of you have providers, you have executors, you have sort of some sort of higher level representation of a workflow, and start to mix different workflow systems together. So you see Parsl speaks to Radical, speaks to Flux, et cetera, in different ways. And the hope there is that people can sort of a la carte assemble the types of technical solutions they need to build their workflows. The second thing we're doing is we're trying to build, as a community effort, some components that can be shared among workflow systems. The first one we're focused on here is we've built the SciJ layer, which is an asynchronous Python library for speaking to different schedulers. So it's almost like that provider implementation in Parsl, but implemented as a new async Python library. We're growing that. We're starting to see contributions from different workflow systems. It's very easy to plug into your system, and if people are interested in using that, would welcome discussion. And then the other thing we're really focused on is community development. The workflows community, as I think we all know, is quite segmented. There are lots of different workflow systems. I think there's a lot of opportunity for us to work together to be able to improve the types of capabilities that we provide users. So we're organizing a series of summits. We had 3 summits last year, 30 odd workflow systems represented, several hundred people represented. You can find out more on that link there. And we're also part of the new Workflows Community Initiative being led by Raphael at Oak Ridge National Laboratory. So with that, I'm finished. Let me know if you have any questions. Everything's on our website. Binder is a great way to get started to understand sort of how the Parsl model works.
Thank you very much. This was very interesting. And we have a first question. Tore, please.
Yeah, very interesting. Thank you. Maybe you answered my question when you got to FuncX, but my question is, can a single Parsl application operate across feed work to multiple systems, or is a given application operating within one system?
Yeah, so the answer is yes. The problem with that answer, and I think many workflow systems would say this, is you can do it, but it turns out that that's not something that your average user can do because it involves setting up SSH connections and dealing with fragility and things like that. So we do have users doing that. In practice, I'd say a lot of people ask for that multi-site execution. In practice, when it comes down to implementing it, they set up the SSH connections, they run it a little bit. In practice, they end up most often just executing on one system. But I think a lot of that's because of the challenges in doing so. So that was a big motivation for why we built FuncX, because a lot of that, it's just so frustrating to have to deal with that type of way of connecting to multiple sites, whereas the FuncX model is almost trivial to do that. You've got this cloud middle person that's negotiating the execution of tasks on different systems, and you've got this endpoint software that's deployed on the different systems that's able to take work and run it and return the results. So basically, like, provides the hourglass sort of model, gets rid of the SSH need, gets rid of the annoying auth requirements. We use the Globus auth model, which is OAuth 2 everywhere. Everything's tokenized, secure, etc. So we have a prototype executor for Parsl that speaks to FuncX to run things, but that's not yet production. So I would, if you're interested in doing that, I'd suggest you just use FuncX vanilla before thinking about layering the DAG on top of Parsl.
Okay, yeah, that makes sense. If I can ask a follow-up, imagine, well, maybe two. The first one is to have a FuncX installation across a number of machines. Do you have to be great friends with the sysadmins on a given platform, or can you come in as more of a user person?
Yes, that's a great question. Something I should have mentioned. So at the moment, FuncX, the endpoint software is actually in user space. So it's user installable, user manageable, single user. You can share your FuncX endpoint with other people, but we tend to not enable that unless we have approval from the admins of the systems, because that'll, especially in the DOE space, violate a lot of policies. But we're focused on that personal user per user deployment rather than requiring sysadmins for deployment. We're building at the moment a multi-tenant version, which will be run by sysadmins and support different users. But at the moment, it's per user, just pip install and get running. So you can run it anywhere. No one even knows you're running it, sort of thing.
Okay, can I ask one more, somewhat related? Imagine that you had FuncX and Parsl running smoothly, purring along on great big LCF machines, which are not the friendliest machines to everybody necessarily, right? And someone else came along with their workload management system that wanted to talk to and send work to an LCF. Now, modulo all the security issues, but could you imagine your Funcat Parsl installation on an LCF being the means by which another system got work onto the LCF?
Yeah, 100%. So we maybe should talk about this generally, not LCF, because LCF has a lot of policies around what's actually acceptable use of their systems. So we use Funkex and Parsl a lot on the LCF systems. Funkex is used a lot for real-time computing from instruments. So when data is coming off like a beam line needing to be analyzed, we use Globus to move it and then run the computing. In that case, we do use sort of multiple users concurrently, where Funkex is like that abstraction that's managing the execution of various workloads at the same time. But our longer term plan is to make that much more of a commodity sort of interface, because you could imagine providing sort of higher utilization of these systems if you were able to, at a more granular level, allocate workloads. So providing a multi-tenant sort of Funkex interface where you're able to actually share the resources behind the sort of pilot allocation that you're using.
Yeah.
Does that answer the question?
Yeah, very much so. Thanks very much.
Yeah, thanks for the questions.
I have some related questions to what Tore is asking. So if I use Funkex, how is the accounting work? So who pays for the resources?
Yeah, so in most systems, when you deploy your Funkex endpoint as a user, you are configuring which allocation you want to be using. So you're setting in that Parsl config object, you say which allocation you want to use, the size of the allocation. So you say there's scaling in there, but it's scaling in terms of scheduler jobs. So you can say, like, I want to use, maybe I'll allow myself to use, I don't know, 1,000 nodes, and I'm going to do it in jobs of size 100 nodes. So Funkex will basically look at the awaiting workload. Once it fills up 100 nodes and it's all running, then Funkex, I'm set up for a Parsl talk, not a Funkex talk. Then Funkex will go and provision another 100 nodes. And if that fills up, it'll go and provision another 100 nodes. Of course, this is assuming an ideal world in which you're not waiting 2 weeks for your allocation to actually go through the system. But that's all sort of queued up in the cloud or on the endpoint, depending on where the workload is. So long answer to say, you configure which allocation you would like to use. And in the multi-tenant model, that will be an argument that's passed in via the cloud service to say which allocation you want to use.
But let's say the user is an independent researcher who is not part of a large collaboration and does not have any resources allocated, let's say on one of the supercomputers. Will he get some resources via Funkex, or does he via his identification already have access to certain resources?
Yeah, so again, in an LCF world, that would not be a use case, because they wouldn't allow that type of thing. That would be against the policies. If you were in, say, a campus cluster and you had an allocation, essentially, so if I wanted to share my campus allocation with you, I would stand up, I would deploy my Funkex endpoint, pip install it, configure it to use my allocation, and then I would set a group of people using the Globus group model to say who would be able to access that endpoint. And I would invite you to that group, Marcus. I could invite Tori, I would invite others to that group, and then they would be able to use that Funkex endpoint without knowing anything about the underlying allocation. It would all be billed to me as the person that configured it.
And if I have a cluster which is not yet part of what you have in Parsl, then I would work with you in order to get this as part of the official Parsl release, because I think you somehow need to define what a different how the details then work in order to run Parsl on let's say a university cluster of some kind.
Yeah, so in practice that's actually really easy, because most of the configuration is just picking the scheduler. So if you have a Slurm, it looks mostly like another Slurm scheduler. So you can actually just run that. So there's nothing we need to do on the Parsl side for that. You would just say, okay, I've got Slurm. Here are the parameters I need to pass through. Here's my Python config that passes those parameters through. The one thing we do like to do is when people start to use a system that we think other people will use, we like to ask them for their config so that we can put it in our docs so that someone can copy and paste it. So if you've got a system that you've configured, it's working great, we'd love to just steal your config and add it to our docs so the next person can copy and paste it. But there's no no technical change. We don't change the code. It's just the docs. If you came to us and said, I've got this brand new scheduler that that I've never heard of before, then in that case, like you invented your own new Slurm model. If you had a new Slurm that I'd never heard of before called something else, then that we would need to actually probably change some code. We need to build a new provider for that scheduler.
Doug has one more question.
Hello, Doug.
Yeah, hi. What's about the timeline for the multi-user version? Because as a service provider, it's intriguing.
Yeah. We've been talking this week actually about what we want to say for timeline for multi-tenancy. So our hope is to have something that's pilotable by the end of this year. Of course, Doug, I think you know this better than most. There's going to be a period there to go through security reviews and go through the discussions with the LCFs to really make sure everything we're doing is reasonable and addresses the policies. So I think pilot probably hopefully by the end of the year. If everything goes well, we're hoping to leverage a lot of the sort of Globus multi-tenancy support in the Globus Connect server package, which has solved a lot of the like user problems, et cetera, et cetera. So the hope is that we'll get it done this year, and then widespread deployment. I think that's an unknown. That really depends on policies, engagement with the different computing providers, et cetera. A lot of socialization, I expect.
Yep, thanks. Yeah, good luck. That'll be the next challenge.
Well, no doubt you'll help me with this, right?
Yep.
I've got you recorded saying that now.
Okay, we have a very last question from Tora. Please go ahead.
Okay, maybe it's appropriate for a very last question, but you're talking about distributed computing, very end user friendly distributed computing, and we work in a landscape in the DOE of the service kind of more friendly to the wider world out there of NERSC being heavily oversubscribed, and then the LCFs. And I'm not even going to ask if any future more open policy could come to the LCFs, but is there any thought of sort of expanding the friendly end of the spectrum that would be really useful and powerful to tools like yours for the distributed computing environment?
Yeah, so I mean, I can only comment on discussions that we have, and I think we have great conversations with ALCF, with OLCF, NERSC. I think they all, I mean, I can't put words in their mouth, but I think they're all increasingly user focused, and they see opportunities in this space to support, not just to make, like to democratize access to these types of distributed computing projects, but I think also to support new types of workloads, because I think we've seen, like, as you see more machine learning, you see more ML steering, you see more real-time analyses. So these types of workloads don't necessarily map well to the current policies we have in place in the large computing centers, and I think there's a realization that those types of workloads are important and need to be supported. I don't think there's answers necessarily to how to do that or the best way of doing it, but I think there's at least discussions happening at the LCFs and even at the sort of DOE level with the IRI work, et cetera, that's going on at the moment. Did that answer the question?
Yeah, it does. It does. Discussions happening. That's good to hear.
Yeah, it's probably been happening for a decade, but we'll keep engaging. I mean, I think everyone knows that this stuff's really important, and hopefully we'll see some progress, small steps.
Yeah.
All right, let's wrap up here. Thank you very much for your presentation. Thank you also very much again to Federico and Tadashi for their presentations. We covered today 3 workflow and workload management systems, DIRAC, PanDA, and Parsl. And we will have our next software and computing roundtable beginning of June, and then we have a summary of the streaming readout workshop of the EIC/nuclear physics community. Thank you very much, everyone, for joining today, and talk to you soon. Bye.